How are you doing, guys?
Been a rough midterms week.
Yeah, it is midterms week. I could guess. I could see that. You just get one midterm with me, so yeah. Guys, I looked in the midterm. I scan. Let me just wait for a minute or two. I know that that's the problem is with a Zoom meeting. You put it at 5 o'clock, and people show up. Compared to class, you can really start, and you can start to write something on a whiteboard. So I will give a minute or two if everyone will show up, and then they'll do more like proper thing. So I looked in the midterm, and I would say overall he didn't do as well as I was hoping for. Okay, so some of you did well, but overall I was hoping because well, to be honest, I'm slightly surprised because I thought if you have this review notes, if you pretty much print out review notes, you can do every single problem there. It was everything was on except question number 2, which sort of require you a little bit of like your own thinking, but everything else supposed to be fully be in this review. So I'm surprised, but
Wait, I thought we weren't allowed to 3D print the notes.
you are allowed to have 2-page notes.
Okay.
You are allowed to have up 2-page notes, so you can like whatever you put in these 2-page notes, double-sided, yeah. It was in a paper about midterm review. I told you all the instructions what to do.
Yeah, I saw it in the guide.
Yeah. Did you use notes?
I did use the notes, but when it came to the first problem, I didn't write out the whole steps when it came to the first problem. So when I was going through there, I wasn't sure how to get the results for the adiabatic
I see.
thing. Yeah.
Yeah, but I pretty much, guys, in the review, I pretty much said this adiabatics is a good situation, and you had all of them, and it was in the nose. So, yeah, I could see no, Ricardo, you're not alone. There are quite a few people who had troubles with problem number 1, and there are quite a few people who had. I would say that people had. I didn't grade it fully, so and I only scan. I looked in everyone, try to figure it out where you stand, but I will try to grade in a weekend, so it will be very consistent, so you'll have all grades by Monday. But overall, at least like 5 people did not do problem 1, at least 5 people did not do problem 2, and at least 5 people did not do problem 3. And problem 3, I'm surprised problem 4, most of you done. You may not done it fully correctly, but it was the one which most of you attempt the most, which I surprised. I thought that number 2, 3 will be the most easiest one. I'm still thinking what to do. I will finish grading, and I will think over a weekend by looking at the grades what I'm planning to do, because I could see quite a discrepancy. I may allow to take you this midterm again, and I'll take the average between 2 scores. If you done well, you don't need to do it. This is what I did before, previously. For example, if you did problem 1 and 2 perfectly, yeah, let's say you have you get 90% high on the problem, you don't have to redo it. You just you only could redo the problems which you did not do perfectly, and you can redo, and I'll take the average scores. Or I will do some maybe a little bit of curving of the score. So I'm not sure. I think it's better probably do redoing it, because in this case at least you learn it and you at least understand how to do it, compared to just okay, move on. But something like that will be in the final. I will put some in the problem, especially such as you did so bad. I want to make sure that you understand, because my goal is to make sure that you learn it. Yeah. So yeah.
I had a question. If we are going to redo it, would it be done similar to some sort of like test corrections, or would it be with the full-blown process where we have to go with the hour and a half to go through the problems we weren't able to do?
So if it will be redo it, you'll have a homework which is due next Wednesday. On Monday, I will finish grading. We'll meet there. It'll be posted. You'll see them probably a week in your grades. I'll let you know on Monday. I may put it on a canvas what will be the like sort of if it will be redo or not, and if you'll see it on Monday. If it will be redo, I will unlock it on Monday after my class. So it will be around 6:30 p.m. You'll have access to the redo, and you'll need to submit the for me redo midterm by Wednesday 5 p.m. So it will be additional work on top of the homework. If it will be redo. Okay. So yes, you'll have access to your homework. Yes, you have it at this point. I hope with redo working at home, you'll all with all this homework solution which you done before, you're all done perfectly. And obviously it will be average. So if people did perfectly well in a midterm, there are a couple of people who did very well. In this case, you're not losing. In any case, you'll have a high score, yeah? But if people who did very badly, they at least will have more than 50%. There are some people who may have around like 20% in a test, which is completely failure. So if they let's say you're doing, you had 100%, in this case, your overall will increase from 20 to 60%, which is less depressing. Yeah. And if somebody is perfectionist and they end up to be having 95% on a test, let's say, and they'll decided to make it perfect because they could not look at it how it could be 95. I only want to have 100. Fine, they can redo it and they increase to 97.5. You know, so it's work for anyone, you know. So most likely I think in it. So I want for you a vote, guys. I'm not saying that I will take it. I will take into consideration. I'm not signing for that. Okay. Who wants to have a redo exam and take the average? Please say yes. And who would will prefer that it will be like sort of if I will do some kind of curving.
Do we type it over in your chat?
You typing in participant yes and no. So people who participate, yes, it implies I want to have a redo. No, I don't want to. I want to have a curving, and nothing. It implies that you don't care, or you couldn't decide.
I just wanted to ask. You said, I think I missed it. You said the grades will be up by when?
I will grade them over the weekend.
Okay, thank you.
So by Monday I should know, and I will give you on a Monday redo. On Monday, if I'll do Monday redo, it will be due Wednesday.
I feel like I'm on a game show. I don't know which one to pick.
I could see that pretty much nobody wants to do curve if they want to do redo, yeah. I could see that most of the people. I'm not looking at names, I just look in the numbers, yes and no. So it's as I know it's not as private, but I will not look in people who exactly choose what. Except as Araceli, who she is the first in the list. So I'm sorry, Araceli, I know you chose. Okay, in this case, I'll clear all. I pretty much got that opinion that 10 people want to have a possibility to redo, and one of them went for a cup. I need a break. I don't know who wants a cup of coffee. Tom. So, okay, I'll clear out all these votes. So I understand, guys. I will probably give you redo. In this case, I know that you may already done this. If you done it, I cannot go back for that. It will be all in honesty. It's as anything which is going right now online. I will ask you to do independently. Yes, you have access to your homework. Yes, you have indefinite, not indefinite, your time limit, but you have a free time and you'll receive your scores. So you can see what you've done, and you hopefully you do it perfectly. But I don't want you to do it together. I want to do it independently. Okay.
Made me real nervous for my grade.
I'm sorry, I will not tell you. You can look on it. You can estimate it how it is if you look how you done it. But I'm just saying that it was quite a spectrum. Some people really did bad.
Would we need to only do what we did wrong?
Sorry?
Would we
So
need
I will write it down on I will discuss one more time on Monday briefly, but I right now I'm taking my time a little bit to talk about it because I know you're all nervous, but I didn't give you the results, but And the reason is, guys, I just want to take time. I looked in it, I see that it will be complicated, and I want to make sure I grade them fairly with exactly that, and want to take my time. And I also was thinking how what is the strategy back. So I decided, you know what, I will not push it for you before this Wednesday. So if you, for redo, if most likely in this case, I will do redo for you. You allowed to use your notes, your homework, your brain, yeah, calculators. If you need to have to do calculation on computer, yes, you can. It was a question if it is a problem to calculate it. But yes, you need to do it by yourself. And I assume that you could not find this problem online because I made them by myself. So, I mean, unless you, I honestly hope you do by yourself. But what you need to redo? Let's assume you done problem number 1, and you done in problem 1 you done 60%. Or let's say problem 1 you got 40%, and let me write it down. I write them randomly. Okay, it's hard. So let's say number 1 you get, let's say, 40 out of 60. Number 2 you done 5 out of 20. Number 3 you done 30 out of 30. Yeah. And number 4 you done perfectly. Yeah, you done, I don't know, almost perfectly, 58 out of 60. And there is a 2 bonuses. Yeah, which is bonus. Okay. So in this case, what you need to do, for example, number 4 you don't have to redo. Yeah, number 3 you don't have to do, it's done. Yeah, you don't need to write it down. So you write number 3 and you can write your score 30 over 30 in a place where you have a test. And in this case, I will double check obviously that it is true, but you don't need to rewrite it. Number 2 you need to rewrite. Yeah, so you need to redo number 2. Number 1, for example, you get 40 out of 60. I'm just making a pretty good student, let's say 40 out of 60. If you had somebody have a score, it's pretty good. It's average. That's average score you'll have. So if you have 40 out of 60, in this case, you want to redo number 1, yeah? And in this, let's say you've done it perfectly. And number 4, these ones, yeah? You had 58 over 60. It's up to you. You can redo it, try to get 60 out of 60, or you can say, I done it, and I had before 58 over 60, and you write down for me in this piece of paper, and I'm using the scores. Okay, you cannot redo for me, think, oh, I'm doing number 1, I done, let's say, 1, 1, 1, 2, I done perfectly, and I only messed up in the next one. You cannot, I want you to rewrite the whole problem number 1. So I don't need to look for each small piece of the problem, yeah? Does it make sense? Because it takes me a lot of time. I need to compare back and forth, especially it's not in paper 1. I need to go and figure it. Oh, you're referring to this one. It's just too much for me. I'm allowing you not to rewrite the ones which you done well. Okay. And yes, you can do bonuses as well to help you out to boost it. Okay. Questions? So.
When will this be due? Sorry.
I will give it on Monday. On Monday, I will give you, over weekend, you'll see it most likely online. And on Monday, I will give you a redo after the exam, after the class at 6:30 p.m. You will have access for this test Monday at 6:30 p.m. It will be your redo. And it's due Wednesday at 5 p.m. Okay?
Thank you.
So that was our plan. Okay? If no more questions, I know I didn't remove your stress. You're still stressful how you done it. You'll just need to live with it and work on your other exams and midterms. But at least you know that there is a path away from that, from your not a perfect performance. Okay. So you partially could sleep. You still sleep at night, but sometimes wake up in a horror. Yeah. Stupid joke. Okay, let's move to the class and let's move to the lecture. Okay, guys, that's it's not the end of the day. We still have 2 more midterms, guys. And if you redo, and let's say you done like 20%, I'm not sure if somebody like, yeah, I think we have a couple of people who did like 20 or 30%, 1 or 2 person. If you get a 20%, okay, if you done it perfectly, you work hard, you got 60 or like 65%. Try to do all your homework, and you still have a midterm 2 and 3, and you could pull up to your grade. If you done well other ones, if you have a very bad day, you still could improve it. Okay. So I will believe in you. And remember, in all of it, what I give you an exam, it's all of in the homework, and I cover everything in review. Okay. I know the review had some issues, but generally it is in review. Okay. If no more comments, in this case, sorry, no, not me. I want to spotlight this video. Okay. You see it? Guys, is it in my paper, is this in Spotlight or not?
Yes.
Okay, perfect. Thank you very much. Okay, let's talk back to what we discussed. We discussed last time about heat engines. I will go over this review, heat engines. And we'll finish this section today. And then we'll move to a new section. We need to cover 2 sections today. So let's talk about heat engines. So we talk about regular heat engines where we have a hot reservoir and we have a cold reservoir. And in this case, it has a temperature T hot and this is T cold. And in here we have our engine. Okay. And what happened, we get heat from hot, oops. So we get heat from hot reservoir. We end up to be dumping some of the heat to the cold reservoir, and out comes the work. Okay, that's a diagram for the heat engines. And we discussed that in this case, for this is a heat engine. That's a review, guys. I'm not talking about this in details. I'm just quickly review. So if we have this as a heat engine, in this case, our efficiency is benefit over cost. It's always like that. We calculate efficiency. This is efficiency. And for us, what is efficiency? Efficiency is a work which we can do. And for us, what is our work? Our work is work. And what is our cost is how much heat we take from the hot reservoir. So it's over Q hot. Okay. Or we can write it down that our work due to conservation of energy is equal Q hot minus Q cold. And what we did before, so and this is how we can write what is efficiency, yeah, for the engines. And that's what we did. We talk about entropy, and we discussed that efficiency is equal than less than 1 minus T cold over T hot. Okay, that's for heat engines. This is what we did last time. And then we talk about this is a just general heat engines and concept of it and how we could work. It could work, for example, as a Carnot cycle. We talk about the Carnot cycle. And that's ideal engine. Ideal. Okay. And this Carnot cycle, this light is not as bright as I wish so. Oh, that's the best what could be done. Okay, so the Carnot cycle, so it consists of 2 isothermal and 2 adiabatic processes. So we have a Carnot cycle. We have sorry. Just adjust papers. Okay, so I'm just trying to adjust the papers to make sure it's everything you can see. So this is our PV diagram for Carnot cycle. And we have situation where we have a thermal compression. This is a thermal. Then we have a diabatic. Then we have a, this is, sorry, it's not a compression. It is a thermal expansion because the volume increase. Then is a adiabatic expansion. Then we have isothermal compression here, and then we have adiabatic compression. So, and here adiabatic. And this is how the ideal situation look for Carnot cycle. And for diabatic, Q is equal to 0. And for the thermal temperature is constant. Yeah. And this is our temperature hot. And this is our temperature cold. And from here, if we use this engine, we can have a situation where we can the most optimal case, and we can have a maximum efficiency. Emax is equal to 1 minus T cold over T hot. Okay, the maximum efficiency. Okay, so we discussed this before, but that's not efficient because I mean that's great. And how you can get the maximum efficiency compared to this one? It's a situation where we have our temperature of the gas consistent with the temperature of the hot and cold reservoirs, and so we don't create any new entropy. And in this case, we have a conservation of the entropy, and we can have a cycle and we'll get a maximum efficiency. But as we discussed, that's not realistic in this to make. So people created like Otto cycle or diesel cycle, which we'll discuss in a second again more in detail. What else we discussed before the exam? We discussed refrigerators. Again, I'm reviewing, so I'm going over this very quickly. We talk about refrigerators. That was number 1 here, heat engines. And here we'll talk about refrigerators. It will be our previous section. It's like number 2, refrigerators. Okay. And in refrigerators, what we have situation reverse. So we have a hot reservoir, which is our like food, yeah. Sorry, hot reservoir, which will be our room, and the cold, it's a food which we want to keep cold, yeah. And this is the situation. And here we have inside of a refrigerator, we have a machine, our refrigerator, which takes heat from our food to make it even more colder. And we dump heat to our room outside, this hot energy, like to the hot reservoir. And to do this process, we need to apply some work. Okay. And we'll talk about refrigerator. We talk about coefficient of performance. Okay. COP is benefit over cost. And in our case, benefit is how much heat we take from the cold reservoir gas. And this is how you always need to think. When you talk about engines, you need to think, what is my work? Sorry, what is my benefit? What do I want? My benefit right now to take heat from the cold reservoir. This is what I want to do. So that's my benefit. And what is the cost? How much I apply the work. Yeah, this is the price which I pay. And if we apply again our entropies of law, we can rewrite it down, and I'll skip this up, and we can write it down that COP could be equal to, first of all, you can rewrite as like work is equal what? it is Q hot minus Q cold, yeah. And in this case, copy could be rewritten in terms of temperatures. Again, we derived it last time in a class how to do it, so you can look in the notes. So that's work for refrigerators, okay? And this is coefficient of performance. And you'll have several problems based on engine and refrigerators, which I'll put for you tonight, so you'll have access to them. And last time we started talking about the last part with real engines, real heat engines, because all of the previous one which we talk about ideal cases, yeah. And we discussed last time Otto engine, like Otto cycle. Again, that was discussed last time as well. And it's a situation where we have a PV diagram. This is which you use for automobile, for so some kind of powering devices. It's real engines which people used. So what is happening here, we have here, we introduce mixture here at this point, introduce mixture, inject mixture, like our fuel. Okay, then what we do compression. Okay, compression of the this injected mixture in air. Then what we do, we ignite our system. We ignite it. And we keep the volume, so it could not go anywhere. So the volume is constant, and as we ignite it, the temperature increase and the pressure increase. Then what we do, we release it out and we produce power. Here we have a power. We let this piston goes, and in this case, it's created workout. And then what we done, we expel here the gas. What we done here, we expel gas, expel exhaust. Yeah. Yes. And we start the cycle again. Okay. And for these engines, efficiency typical was 1 minus V2 over V1, gamma minus 1. And what's that? That's, you can find it, what is gamma, guys?
F plus 2 over F?
Yes, it's F plus 2 over F, yes. Okay. And if you know that it's a diatomic gas, what is it for diatomic gas?
It's
5.
For diatomic gas, F is 5, and in this case, gamma is
7 over 5.
7 over 5. And if it's a monatomic gas, F is equal
3.
Perfect. And it's in this case, it will be 5 over 3. And typical ratio for compressed gas, which when we use Otto cycle, it's V2 over V1 is roughly equal to 8. So in this case, the efficiency which they give is 0.56. Okay, 56%. But in reality, that's ideal, yeah. In reality, automobile engines, automobile engine produce efficiency 20 to 30%. And why is it? Because we have a friction. It's not go smoothly. We have a conductivity heat loss, so from connecting with environment, and we have not we're not completing full combustion cycle of the fluids. And in this case, we also lose some efficiency. So that's ideal, zero of having 56%, and this is reality. Okay, that's a theory. This is experiment. Okay, so that's what we covered last time. So I will talk quickly about 2 more cycles. Sorry, I went over this quickly because we discussed this before, but I want to make sure it's all refreshed for you. So I want to talk about two more. Oh, I want to talk to you quickly about generally about cycles. Do you know who created the first engine, steam engine? Well, like the one which we discussed the concept of like pressing the gas, like and the piston.
Henry Ford?
He implemented it, but before that, it was a guy who Watt. You know, like the Watt, the same as you did with electricity, yeah.
James Watt?
Yes, and in 1781, and he created a steam engine with a piston. And so he developed this because it was an idea of using piston and a gas and you can produce the work. But then he wants to patent it. And then it was a problem. So he created this engine, but then you need to transfer this energy to do something, yes? To move some kind of machinery, yeah? Compress something which they want to replace this old machinery. What people could do physical work, they can replace it with machine, yeah. So that's process of transferring this piston energy from this piston to machine. That was a problem. And when he was trying to patent, the regular concept of the gears was already been patented. So he developed this awesome steam engine, but he couldn't patent it. So he was spending several years develop different types of the gears, and it's called sun and plane gears. He developed out so he could patent his steam engines and then could be used. So sometimes this has happened. You develop a new concept as an inventor, and then you try to patent, but the small piece of the concept which you use is based on someone else's patent, and you couldn't patent it, yeah? Or you need to have a license, so you might need to come up with something new. And as discussed before, that was originally all these engines were used is like in mines to remove the water from the mines, or in a factory to do like hard work. But it was mostly done in the industry. It's later they start to use these engines to like machines, like to like trains, you know, whatever it is. It was done much later. Originally, it was using to do the hard work, for example, pumping water. And I don't know, maybe some of you heard, you know, this silly TV series called Padlock or something like that on Amazon about Cornell, something like that areas in Portlag, whatever it is. Okay, never mind. So it was about mines. It's like very big in Amazon area. I watched a couple episodes only, like 5 or 6 series there, where they're talking about mines and they remove tin from the mines, and that's really story where they create engine. And one of the first engine which Watt created was used there in these areas to remove the water from the mines, and you can use old mines to get more materials out. So a little bit of side story for you, because sometimes it's not only about math. Okay, let's talk about diesel cycles. Okay, let's talk about just my camera. Okay, so diesel cycle is much more efficient. You can hear in the car because they have a diesel engine, yeah? It's more efficient. And the reason behind it, because you can compress volume much more, because you if you take the uncompressed gas to compressed gas, V2 or V1, you can reach around like 20. So in this case, you can have more efficiency. And what is done is the problem with the Otto cycle is that we inject liquid, yeah, this fuel, and then we compress it. And as if we compress it too much, in this case, it could spontaneously ignite, yeah, and we can could ruin equipment. So we want to ignite in particular point when we want it. And what it's done in this case, you first compress the gas, and then you insert the fuel, and that's the difference. Okay, so so you compress on the air. So if you look in a cycle, it's easy to draw, but it's a little bit maybe hard to explain. So what's happened? You compress air. You compress air, and then you compress it adiabatically. Okay, so compress air, and then when you reach this point, that's a point where you inject your petroleum, yeah, and you ignite it immediately here. And then if you inject it and you ignite it, in this case, you start to heat up, obviously, reactions happening, and the volume goes while keeping the pressure. And then when we reach this point, we release it out our pressure, and we let the pressure drop out, and here we come up to have a power. So at this point, we have a power. Okay. And then here we come back to original situation. We remove the old gas and like all the liquid, and we start the cycle again. So idea is we compress only air, compress air to prevent spontaneous ignition, to prevent spontaneous ignition. And then we do injection and ignition as piston begins to move outward. So we do injection and ignition as piston begins to move, as piston begins to move outward. Okay. In this case, we can compress gas even more. We can compress it more than 20 times from this point to this point, because otherwise with gas we cannot do it. And in this way we can get even more efficiency. And efficiency of the diesel cycles is approximately, of machines, it's like 40%. Efficiency. Okay. And the final one, I will talk very briefly. I will talk about steam engine. They use a totally different process compared to gas. Here we compress gas and we insert some liquid. Here we use a steam. So we cannot use our PV diagrams to do that, to calculate what kind of work we've done, because we're talking about water. We have liquids. We are not having ideal gas. Okay, but idea is that this is our PV diagram. We have we are starting here. We move forward. We pump the water pump to high pressure. Here, pump. Okay, so it will be number one. So number one is water pump to high pressure. Water pumped to high pressure. Then we use a boiler, and what happened is water, here we have a boiler. So number two, this water goes to the boiler and it's heat up at constant pressure. so it will flow into boiler and heat up and heat up at constant pressure. Okay, so it's our step number 2. Then we turn to the turbine. We're doing the work. We start to do this work. This is our turbine. This is step number 3. Okay, this is a period of time when we do the work. So steam hits turbine and expand adiabatically and it's cooled down. So, and the turbine moves. Yes, you hit the turbine, turbine's move, it's cooled down, it's done the work. So this is the point where we get our work here. Power. Okay. So steam hits turbine. And it expands adiabatically and cool down. And adiabatically. And temperature goes down. Okay. So if the temperature goes down, what happens with the steam?
Turns to water.
Yes, so it will turn most of it to water, but not fully. And then we'll do the last cycle. We use condensers to make sure that we go back fully to the water. Okay. So number 4, condenser, use condenser to cool down mixture. Okay. That's pretty much. And this is called steam engine, or sometimes it's also called Rankine cycle. Okay. And this is approximately how the real refrigerator use. They use pretty much the similar to steam engine, but in opposite direction. Okay. Which makes me wonder, is this a reason which I need to check out? Is it the reason why all water evaporates in a refrigerator? I don't know. I need to check that out, because you know, like when you keep the water in the refrigerator, it's slowly, if you have like fruits and this, they sometimes like vaporize some of the older refrigerator, at least it become drier, and some of the place they condensate. No, I don't know. Never mind. Sorry. I need to check this out. I say something random and I need to check that out before I'm telling it for you. Okay. Now we're done with this section. We're moving to a new section, chapter number 5. Any question about engines? You'll have a homework problems on it. Okay, most of it was review, and you will most likely, well, I think all the problems just in regular engines and refrigerator. Okay, so let's talk about free energy and chemical thermodynamics. Okay, that's your next chapter in the book. Okay, so first we'll talk about free energy. Okay, and first subsection will be thermodynamic potential. Okay, and first subsection under thermodynamic potential will be enthalpy. We go for quite a few subcategories here. I'm just trying to keep the categories so you can follow it up, okay? So let's talk about enthalpy. We discussed this before, yeah? What is the enthalpy? We defined that it's, what is the free equal signs with free lines mean?
A definition?
Yes, yes, it's a definition, just in case if somebody doesn't know, I forgot. So enthalpy defined as energy plus PV, yeah? And what does it mean? It's a total energy which is needed to create the system out of nothing and put it in such an environment, okay? So total energy which is needed. And why I'm writing down, guys, because we'll talk about other types of energy and we want to make sure that it's all in one place and you're not lost, because you'll see that they're almost same but slightly different. So total energy which is needed to create the system out of nothing and put it in such an environment okay. For doing that, we need to displace its environment and establish its volume and pressure. Okay, so if we want to create a glass of beer in front of in my hands, so in this case I need to displace the air here and get the energy to put this beer here, yes? But I also need to take the energy of the air around it, okay? So that's enthalpy. Let's talk about another terminology which we'll talk about number B is Helmholtz free energy. Helmholtz free energy, or sometimes it's called free energy. This is enthalpy. Okay, and it's Helmholtz free energy. So idea is, yes, if I want to create a glass of beer in my hands, yeah, nice and whatever I wanted, yeah, I need to displace an energy and environment here and put my beer. And it's quite of a lot of energy. But also to create this process, I can use some of the free energy from environment. Just because of this, due to temperature difference, the heat will flow from environment to balance it out and will help me to create this object where I want it. Does that make sense? Because we discussed about temperature difference and energy will for free will go in this environment. So the system can extract some energy from environment. Okay, for free. Okay, due to the temperature difference and heat flow. Due to temperature difference and heat flow. Okay, and here we defined it as F. Don't ask me why it's F. It's always confused me why they use these letters, but it's, I know it's kind of confusing because Helmholtz is started with H, but it's F, and enthalpy with start with E, it's started with letter H. So I don't know. We just need to remember these letters. It's defined as U minus TS. So the energy which system could have, it's need this energy, yeah, to put the system, like to have this system. The system needs this energy, but some of this energy can come from environment, so we can subtract this energy because this energy we can get for free. So it's total energy needed. So this is called, this is a Helmholtz free energy. And it's the total energy needed to create a system which is our U, yeah, minus the heat which we can get for free from environment. Okay. So what is a T? T is a temperature of environment. And S is system final entropy. And we use this formula when temperature in volume is constant. Okay, just a small note. Use when temperature in volume is constant. Okay. So we have this extra energy which flow from environment, yeah, and it could, how it could flow? It could flow spontaneously as a heat. Okay, so I want to make a comment that the energy Tc can flow in spontaneously, as heat. Okay, so the energy Tc can flow spontaneously as heat, and this F, heat-free energy, measures the useful work obtained from a closed thermodynamic system at constant temperature and volume. And this F, which is Helmholtz, yeah, free energy. I know, guys, it's slightly confusing, and I will confuse a little bit more because I will introduce, like in a minute, one more concept. But bear with me. It's like I will put all of it together, and then we'll try to sort it out when we use what, okay? Because right now it's a little bit overwhelming. I'm throwing you enthalpy, energy, entropy, Helmholtz free energy, and I will talk in a few minutes about Gibbs free energy. Just be with me, okay? So F Helmholtz free energy measures useful work. Okay, obtainable from a closed thermodynamic system. Okay, at constant temperature and volume, at constant temperature and volume. So CV constant. Okay. As I already wrote for you, so a small note here. Okay. And finally, this F is minimized at equilibrium. F, this Helmholtz free energy, yeah, is minimized at equilibrium. When entropy is the maximum, yeah. That's the point of equilibrium. Okay, so we talk about, so Helmholtz free energy, it's the energy of the system which it have minus the energy which it could get for free. Okay, because for example, I have the energy of my glass of beer, but energy of this air surrounded which I could get for free, we need to subtract it out. Yeah, we can get it for free from this environment of the air. Okay, now let's talk about Gibbs free energy. Or it's called free enthalpy. Okay. So it's defined as G and it is U minus Tc plus Pe. And we use it, like one to will be consistent, use when T and P constant. So the Gibbs free energy measure work you need to create the system or work you can recover when system is destroyed. So I want to use this magic to create this beer in my hands. Yeah, I want to do this trick. So how much energy I need to do to create this glass of beer? We talk about enthalpy. Enthalpy, it's how much energy it's needed to put this beer and displace all the environment around it. Yeah. But now I also I'm a smart magician. I could get some of this energy from the heat flow from environment, yeah? So I'm subtracting it out. So I need only put this amount of energy to create this glass of beer. Because I need to have, this is an energy of my glass of beer. That's the one which is related for me to displace all the environment and get proper pressure and volume. And that's how much of energy I could get for free from environment. And so this is how much energy I totally need to create my beer. Does it make sense? Or whatever it is, ice cream or rabbit. I always remember Arthur who's having a glass of beer during the exam. So
Beer's good.
okay. So measure work you need to do to create a system. Okay. Or work you can recover when system is destroyed. At constant temperature and pressure, obviously. Okay. So what Gibbs free energy measure, it's a measure usefulness of the process. It measure usefulness. Or process initiating work obtainable from a thermodynamic system at constant temperature and pressure. Or process initiating work obtainable, or it's a measure of usefulness, or process initiating work obtainable from thermodynamic system at constant temperature and pressure. Okay. So now we can, number D, which will be short, we could write nice thermodynamic potential relationship. And you can see it by yourself. We start here. We make this nice square. And if we have here our U, and if we add PV, what we'll get? We'll get H. If we subtract, oh, sorry, one pencil. If we subtract TS, we get, oh, sorry, one pencil. We'll get F. Yeah, we get Helmholtz free energy. So and if we add PV and subtract TS, we'll get Gibbs free energy. So it's a very nice table which put all of them together. So instead of writing hundreds of the formulas, you can write this small square, and it's pretty much related to one with another. But obviously you need to understand what does it mean. Okay. So let's yeah. I know we'll not be able to probably finish today when we talk about examples, when we are talking about chemical reaction, and we will give examples when we have a water and a break up in hydrogen, oxygen molecules. You'll see why we care about it when we're talking about this energy comes out. But let's go back here again. U, it's energy of the system. H, it's if we want to create the system, we also need to adjust its pressure and volume to put them in the system so they survive. So we need to remove environment and put this object there with this energy U. F is we have our energy of the system. We want to put object with this particular energy, but we can have some free energy from environment due to the heat flow, due to the temperature difference. And in this case, this is take care of that. That's F. And G is if we want to magician and we want to be a smart magician and we want to put system in this particular location, we will get some free energy from the environment, plus we'll balance out pressure and volume. Okay. So now let's talk about next part. Let's talk about change in Helmholtz free energy. E. We'll talk about change in Helmholtz free energy. Delta F. Okay. So we're talking about when we talk about Helmholtz, what we're talking about. We're talking about Helmholtz free energy. We're talking about system where we're talking about changes. Just in system when temperature and volume is constant. Yeah. This is when we talk about Helmholtz free energy. And so in this case, if we're talking about Helmholtz free energy, delta F is equal to what? We're supposed to have delta U minus Tc, yeah? And it's delta U. And what is the temperature? Temperature is constant, yeah? So that's why it's T delta S, yeah? Because temperature is constant. And what is delta U? It is heat plus work minus T delta S. Okay. So now, if we're doing the process and we are not creating new entropy, if we have a quasi-static reversible process, yeah, if no new entropy, okay, during process, if no new entropy is created, so we have quasi-static reversible process, yeah. If we have this type of process, then heat is equal to T delta S. We did this before, yeah? For quasi-static reversible process, we know that heat is equal to T delta S, yeah? That was the definition of our temperature. And in this case, if heat is equal to T delta S, what will be our delta F? Our change of the Helmholtz free energy is equal to work. Now, that was a particular case. Now, if new entropy is created, okay, in this case, we have situation that T delta S is bigger than heat, yeah? Does it make sense? Yeah, we have create new entropy, so process is irreversible. In this case, this formula is not valid, and we have this situation. So we have new new entropy is created. In this case, if we plug in there in our formula for delta F, we can get that delta F, the change of Helmholtz free energy, is less than work. Okay, so in general, we can write it down and Helmholtz free energy, the change of Helmholtz free energy is less than equal than work at constant temperature and volume. And I want to point it out that work includes all work done. What does it mean by all work done, guys? All type of work, yeah?
We could have
Yes?
we could have work done by compression or by any other like object like doing work on it.
Yes. So we're talking about every types of work. Remember, we talk about work and other works, yeah? So we're talking about not only through compression expansion done, but also done by environment, yeah? All work done on the system. Okay. Okay. So now let's talk about next point F. Here we're talking about the changes in Gibbs free energy. we'll talk about delta F. Oh, sorry, delta G. Sorry, delta G. Delta G. So that happens if system is at constant temperature and pressure. We use this concept of Gibbs free energy if system is at constant temperature and pressure. That situation when it's useful to use Gibbs free energy. Okay. So delta G is equal to delta of U minus T delta C, T C plus PV. So we can apply this condition and we can get it as delta U minus T delta C plus P delta B. And from that, we can write it down that it's equal heat plus work minus T delta S plus P delta E. And as before, heat minus T delta S depends on reversibility of the process. It's a bigger or equal than 0, and it depends on reversibility. Of process, if we create new energy or new entropy or not, and W include work done by environment, yeah. Okay, as we discussed here, work include all of that. So what we can do, we can write our work as minus P delta V plus work of others, yeah. Due to the change of the compression or expansion of the gas plus work of others, yeah. So in this case, we can write it down. You can see that these components give us a sign big, give us sort of could cancel out. We put the proper sign, and these ones could give us work of others. So we can get that delta G is less than equal than work of others. Okay, at constant temperature and pressure. And delta G is equal 0 in equilibrium. Okay, why it's equal to 0 in equilibrium? Yeah, because we discussed that. Yeah, because we have situation where in this case we have no new entropy. Yeah, and work of others we don't have it. And what is the work of others, guys? It could be any other work, yeah? Like, for example, electrical work, yeah? And so on. Something which is not related to compression and so on. Okay? Okay. Delta G is used a lot in describing chemical reaction. And we often need to do it, and you'll have a homework where you'll need to do something similar. So to find delta G, what do we need to do? First, we need to measure delta H. So it's a heat absorbed when reaction takes place at P constant and no other work. Heat absorbed when a reaction takes place at pressure constant and no other work. Second, we need to calculate entropies of the initial and final state. Calculate entropies of the initial and final states. And to do that, we use by using tables for entropy. In chemistry, they give you tables of entropies. People already done this work for you, and which derived from heat capacity. Okay. So we measure delta H, which is heat absorbed when reaction takes place at constant pressure and no other work. We calculate entropy of initial and final stage by using tables, and we'll apply it in a second. And finally, we can compute delta G, which is equal delta H minus, delta H minus T delta S. And I want to give a quick example how we can do it, so we can sort this out. So let's look at the last one. It will be example. Let's look on a chemical reaction where we have a water and it's break up on hydrogen plus oxygen. Okay. So we need to find delta H, and we want to find the change of enthalpy for this reaction. We can find it from table. We can find that delta H is equal to 286 kilojoules. So it's the amount of heat we would get if we burn 1 mole of hydrogen atoms and we do reverse reaction. Okay, so we have a formula. What happens if we have a hydrogen atom and we burn it in air, 1 mole of gas, and in this case we'll get our water, and from that we can find how much heat is needed, and we'll do reverse reaction because we're going in opposite direction. Second one, we want to find out P delta V, because we need to push atmospheric pressure to get these gases. It's push temperature. Oh, sorry, push atmosphere away to get space for produced gas. Because before we have a water, and water that takes just a little bit of space, yeah, just tiny bit space, and now we produce a gas and they take more space. So we need to push the atmosphere away. Third step, we need to find what is our delta U. Delta U is equal to delta H minus P delta V. And we can plug it in, and we can get 282 kilojoules, and it's energy which system keeps. Okay. Now we want to find the entropy because we want to find what is the Gibbs area energy. So we need to find entropy from table. we use the tables, and from tables we can find what is the entropy, and entropy of water is equal to 70 joules per Kelvin. Entropy of hydrogen is equal to 151 joules per Kelvin, and entropy of oxygen is 205 joules per Kelvin. So in this case, we can find out what is T delta S. What is the temperature? With the temperature of our environment. Remember, I wrote down here for you when we defined it that here Ts, when we use it first, it is the temperature of environment and its system final entropys. This is what we do here. So here's the temperature of environment. So it's our room temperature. And we sum up the entropies, what we have as a result, hydrogen, oxygen, 131 joules per Kelvin. We have 1 mole of hydrogen, and we have a half mole of oxygen, so we have it 1/2 of oxygen. And we need to subtract original entropy of the water, 70 joules per Kelvin. So we get 49 joules per Kelvin. Okay. Oh, sorry, 49 kilojoules. Sorry, I'm trying to write it down. 49 kilojoules. So that's C delta C. It comes in terms of heat. I'm almost done, guys. Almost done. It's almost the end. Then system need. We can calculate that system needs Gibbs free energy delta G, which is equal to delta H minus T delta S, which is equal to 237 kilojoules of energy to make this reaction. Okay. And how this delta G comes in? This delta G comes as electrical energy. Okay. So it's electrical energy. It's other work to do reaction. Yeah. So now let's do a diagram and see how we can do it. And guys, I'm a few minutes late, but sorry, we discussed about your exams before that. So we know that we need our delta U energy here to create a system. We should have a 282 kilojoules. Yes, this is our delta U. That's how much our system needs of energy. Yes, delta U. So what we got here? We put delta G here, which is 237 kilojoules in terms of electrical work. We have another source here in terms of heat. It just gives us this energy. We can need to apply in terms of heat. Okay. And for this reaction, what happens is, well, we need to leave some of the energy. It's P delta V, which is equal to 4 kilojoules, pushing atmosphere away. Okay. So here's our reaction going from water to hydrogen and oxygen. So we this reaction required this amount of energy. So to do that, we need to dump so much electrical energy, some heat, and we need to push atmosphere. So that's the process how we can get it, but we can do reverse reaction, and that's what they use a fuel energy, fuel cells, and it's like new types of energy, like, you know, like renewable energy. I know you all lost attention, but I think it's the most interesting part while we're all doing this whole derivation here. So, you know, like all this new type of energy where environmentally friendly, because here you can have, if you reverse this reaction and you go from reverse reaction and you go from hydrogen plus oxygen, and oxygen is in air. So if you put hydrogen cell and you have oxygen in the air, what you end up to be, you'll end up to be producing water, which is perfect waste. Water is in air, it's absolutely fine. And we can extract from this reaction, we can extract 237, which is huge, kilojoules of electrical work. Okay. And from one mole of hydrogen. And that's reaction used in fuel cells. Okay, and for this fuel cells, they're quite efficient. They have only waste or energy, which is 17%, and efficiency is 83%. So it's a very efficient fuel cells where you have a hydrogen and it's react with oxygen and it produces electrical work. Okay, that's how little bit. Yes, I know somebody typed me time. I don't know. Yes, it's 6:28. Yes. Okay. Okay, that's it. I know I keep you for longer. That's done. I just want to finish it up because you'll have it in the homework. And next time you also want to talk about exams during the class. And I just want, otherwise we'll be just behind, and I'm sure we'll discuss this again for 15-20 minutes. Otherwise we'll be all behind this. Okay. Guys, I'm done with the lecture. I don't have a grades, but I know that some of you may be very anticipated what is my grade. If you really want to, I could give you a roughly estimation how many problems you did correctly and right. It will not be a full graded, but at least you know approximately what to expect if you really want to, okay? So if you want it, you can stay there and behind this meeting as everyone leave, and then I'll put who wants to be in the waiting room and one by one bring you in and discuss with you like in 30 seconds, like in 1 minute each of you. If somebody wants it now, if they couldn't wait until Monday. Okay, for everyone else, I'm saying bye.
Thank you.
Bye, guys.
Thank you.